Hi, everybody. Welcome once again to RAG Masters, a show about, you guessed it, retrieval augmented generation. I'm Neil Katz, 20-year tech entrepreneur. With me, as always, my co-pilot, human co-pilot, not AI, Daniel Warfield, a data scientist and a RAG engineer in his own right and a phenomenal online educator. Daniel, what's up?
Nothing much, except we're going to talk about one of my favorite topics. So I guess a lot. We're talking about fine tuning today, and I guess in a RAG context. What do you know about fine tuning? Like, what's your lowdown?
What's my lowdown? So the way I think about fine tuning in the RAG context is the language model we use for completions. Sometimes we might want to fine tune the information that it knows. Instead of using just a general model off the shelf, you want to add new information to that model and try to train it a little bit on your extra content and context. In the early days of RAG, I think people thought about these things as an either or, that if you wanted to build an AI application with your data, one path was RAG, where you store your data separately and you introduce it as context at runtime. And another approach would be you try to take your data, turn it into a large amount of question-answer pairs, and then fine-tune a model and not need the RAG step. But I think from my perspective, what we're coming to see is these techniques are actually compatible. They're not either or. You still, I think, always need RAG. And that's not just because I had a RAG company, but because I think you always need to store your documents separately. I think it's always easier to add content on a continual basis to a RAG database. You can't really do that with fine tuning. It tends to be more complicated. It tends to need more pure data and not the sloppy data we often see in RAG systems. But I think for a lot of companies, especially in regulated industries, where they want to run their own local versions of a model, they don't want to call outside their own cloud to OpenAI or someone else. They kind of prefer, and I'm talking about like hospitals, banks, and so forth, they kind of prefer running their own version of a Llama or Mistral or something else. Those guys, I think, are really interested in fine-tuning those models to just be more responsive to the kinds of baseline questions they know they're always going to have in finance or always going to have in healthcare. Still need RAG for like, hey, what's this person's medical file? What's this report? But there's some baseline things that everyone's going to ask that you can fine-tune into a model. I'll stop there. That's the depth of my knowledge. How you do it, I think you're about to tell me.
Yeah, I think that was an amazing summary. So I think we're basically going to be covering that, except we're going to be zooming in. So I got some slides. Today we're talking fine tuning. But before we talk about fine tuning, I want to take a half second to talk about training, because I think it's important to understand what training is before you get into fine tuning. So
Sure.
Imagine we have like the simplest model in the world. It's a model with one parameter, and that's a weight. And the output it's in tiny letters. It's the input times the weight, right? So if you have a weight of 3, your input's 2, your output would be 6, right? So
that is very small. I got to agree with you.
Yeah, I got a lot more information, so that's why it's so tiny. I maybe should have made it bigger.
Yeah.
So we train this process. We train this model via a process called stochastic gradient descent, which is a big word for a relatively simple concept. So you have a bunch of data that you want to emulate, right? So maybe you have, a bunch of data of like my input's 3, I want my output to be 9. My input's 2, I want my output to be 6. This is your training data. And you might notice there's a really complex relationship between the input and output. The output is the input multiplied by 3 in this example. Of course, this is very simple, but you can imagine you have a picture and then you say it's a dog or a cat, or you have some time series signal from a motor. Is it braking or not? Like, the relationship can be very complex. So you can't just say the relationship is 3. You have to find the relationship. And that's where stochastic gradient descent comes into play. So when you create your model for the first time, you initialize the model with random parameters. And we only have one parameter, so we're just going to initialize it as 7. So W is equal to 7, right? So we grab some input. Maybe it's our first input. So our input's 3. We pass it through our model. We get out 21 because our weight is 7. But that's wrong, because we know what the output should be. The output should be 9. So we can calculate relatively easily, very easily actually. 21 is bigger than 9, so the output should be smaller.
Okay.
Because the output should be smaller, the weight should be smaller. Because when you multiply something by a big number, it gets bigger. When you multiply something by a small number, it gets smaller. So what you do is you reduce the weight. And then you give it another example. You say, oh, it's still too big. Let's reduce the weight again. And you give it many, many, many examples over and over and over until eventually it converges to the weight that you want. That's what training is in a nutshell. Like these giant models, ChatGPT, all that jazz, they're doing that a trillion times.
Mm-hmm.
So
kind of the simple math underneath a very complex machine.
Yeah, and I think that's what's really cool about machine learning. It seems like it's complex, and it is complex, but it's complex because of how big it is, not because there's anything fundamentally complex about it. It's actually fundamentally, the entire discipline is very simple. So now we get into the complexity, and we're building on top of this concept. So stochastic gradient descent, like this incremental adjustment of parameters, you can think of it as a traversal through a landscape. You usually don't think of it as discrete parameters. So like if we take our W, when it was equal to 3, it was like perfect. But when it's bigger, it's bad. And when it's smaller, it's bad. So like our badness gets bigger the further we get away from W is equal to 3. And that's what this graph represents. So this landscape of values, when you train a model, you can kind of think of it as traversing through this landscape. So you have some model that's randomly defined, and you don't like know this entire landscape like we do, because it's we have this simple thing, but like no one knows, given a giant model and you give it some image, what will happen until you run it, right? So you don't know this entire landscape. You have to traverse this landscape kind of randomly, right? So you have this randomly initialized model, and you say, oh, it's too big, we need to make it smaller. Oh, it's too big, we make it smaller. And then it goes, oh, it's actually too small this time, let's make it a little bit bigger. And then you descend through this landscape. So the idea of stochastic gradient descent is this stochasticity is there's an element of randomness to it. You don't know where you are or where you're going to end up. A gradient is basically saying, calculate if things should be smaller or things should be bigger. It's like a math speak for just calculate if things should go up or down. And then when you find where down is, go that way. And that's stochastic gradient descent.
So let me ask you, this works because, tell me if I have this right, because you have a phenomenal data set of like perfect question answer pairs or well-labeled images in the case of these image models, so that you do know what the actual answer is supposed to be. And that way you can traverse, as you say, through these incorrect weights until you get to some optimal weight.
Exactly.
Which gives you the right answer, because you kind of know what the answer is ahead of time, at least for the initial training set.
Exactly. That's exactly right.
Got it. I'm on board.
All right, cool. So that's training, right? You descend down this landscape through stochastic gradient descent. There's different ways to do it, different modeling strategies, but 99.99% of the time when someone talks AI, they're talking stochastic gradient descent. So now let's get into fine tuning, which you'll be happy to know is exactly the same. So it's the same process.
Okay.
It's the same exact process. You're descending down this landscape. And this actually happens a lot in AI. The more you learn about AI, the more you realize that there's a bunch of things that people call different things, but they're actually the same thing. And the reason they're called different things is usually the intent behind it, like the general idea. And that's kind of derivative of the literature rather than like actually what's going on under the hood. So training and fine tuning, and also sometimes training is called pre-training, when you will fine tune later. All these things are essentially the same operation. But you can kind of build on them, which we're going to talk about. So generally, like the most fundamental approach is you have a random model. So you create your model for the first time and you give it a bunch of data and you train it. So then you have a model that knows something, right? You've trained the model to know something. It's updated its parameters to be good at something, some general thing. And then the idea of fine tuning is once you have a model that's good at stuff, it might not be good at specifically what you need, but it's good at something. It has some general knowledge about some related task. You can take that same model and update it based on a different data set, and then change that model that knows something about one thing into a model that knows something about something else.
Okay.
So that process is fine tuning. You're taking this model that generally knows about information, and you're turning it into a model that knows about something specific. And I have an example that's, I think, maybe a little more concrete. So imagine you're trying to make a model that's good at coding, right? And you have some random LLM that you've never used before. You just created it, and you have a bunch of text data. These might be Wikipedia articles. These might be, I don't know if Quora allows for it, but these might be books. Like there's, a bunch of text data. So
probably something you legally scrape from the internet without paying any copyright.
Yeah,
can we exactly say that?
Yeah. And it can be really random data. It can be information about all sorts of stuff. And that's actually a common paradigm. Usually you pre-train on very large data sets, and then you fine tune on comparatively smaller and more tailored data sets. So you take all of this text data off the internet and you train a language model on it. So then you get a language model that understands text. It understands English. It understands, some stuff, right?
Yep.
What you can do is you can take that model that understands English, that understands language, and you can give it tailored data sets for coding specifically.
Okay.
Then you can fine tune it, and then you end up with an LLM that's good at coding specifically. But what's really cool is it inherits some of the linguistic knowledge that it learned through the pre-training process. You can imagine how much knowledge of English one has to know to be good at coding. So it's useful to have a model that already kind of understands English before you try this maybe somewhat more complex task of learning how to code.
So how should we think about, so why doesn't fine-tuning basically erase the original training of the model? Why is it additive, not a replacement?
That's a great question. And the answer is sometimes it does. There's a quirk of fine-tuning called catastrophic forgetting, where if you fine-tune a model incorrectly, it can learn some important information that it learned in the pre-training process. That is entirely possible. And actually, we're going to be talking about a trick that kind of helps mitigate that from a design perspective. But fine-tuning is kind of a difficult thing to do. And actually, that's the next thing we're going to be talking about. When do you fine-tune and how do you fine-tune?
Okay.
So before 2018, the answer of when do you fine-tune was more or less usually, right? You pre-train and fine-tune. That was what you do. And then after 2018, it was sometimes it's really good, but usually you don't need to. So really kind of how I think of when do you fine-tune, like to fine-tune, fine-tuning's hard. We just kind of talked about it. It's an extension of the training process. And a lot of people don't really know how to do training properly. And you can erase or undermine the quality of the model through the fine-tuning process. Yeah. So you can undermine the quality of an LLM through fine-tuning if you do it incorrectly. Also, at the end of the day, 99% of the time, bigger models are better. So instead of fine-tuning, maybe just use a bigger model if it's available. And also, the bigger the model you're using, probably the harder it is to fine-tune. And also, in like GPT, after GPT-1, like GPT-2, GPT-3, a lot of research came out that language models are few-shot learners. Instead of fine-tuning, you can do prompt engineering. You can give it examples and then change the model that way. So a lot of the time, it's unnecessary to fine-tune. That said,
I'm glad we're going to spend the next 20 minutes talking about how to do it then.
yeah. That said, there are good reasons to fine-tune, right? Like it's not all bad, right? Okay. So if you have a large, high-quality data set, right, of examples that you want to emulate, then fine-tuning can be much more attractive. Like imagine if you have 200,000 examples of question answer pairs for your company because you're talking about some specific, topic. You can't prompt engineer that into the model, right? Sure. That's too many examples. So in that specific context, fine-tuning may be very attractive. Also, if you're using smaller models in the first place, if you don't want to upgrade to an expensive, maybe proprietary model that's hosted on the cloud, maybe you have security concerns, you need a smaller model, or for financial reasons, you want to use a smaller model, maybe you can't just upgrade. Maybe you want to improve the model for your use case. And then fine-tuning can be a very, very, very good approach. So it's very relevant still. Fine tuning is very relevant, but there's a give and take between fine tuning and more common approaches.
So you talk about these needing thousands of question answer pairs, which, I think in most business contexts is not a practical thing. Very few businesses can organize all the chaotic information inside their company into 10,000 beautiful questions with perfect answers. But when I think about, and tell me if the right example, when I think about how OpenAI and the other models were able to pretty quickly become very good at taking the bar, taking legal tests, or taking MCATs, taking medical tests, that this was an example of them using fine tuning on their own models because they were able to have, from the academic literature and all the tests that are available, thousands or tens of thousands of perfect question answer pairs for legal and perfect question answer pairs for medical. And so it became this kind of perfect way to add some very specific new information to a model, and they become really good at a certain domain. Would that be a correct example?
I'm actually not sure for that specific one, because
added to the whole data set of the model instead of fine tuning.
Yeah, because
Made it.
Like after like GPT, I have to review the GPT papers to answer that perfectly. GPT-1 was generative pre-trained transformer. That's why it's called GPT. They had fine tuning built in to the architecture. Like that's like the pre-training implies fine tuning. So the first one, like pre-training was like part of it. Later ones though, they got away from this concept of pre-training and fine tuning and just made bigger models that looked at more data.
Okay.
So generally speaking, the later GPT models employed fine tuning less as an important, fundamental, part of the training process. But for like those like impressive results that we talk about with like, the bar and like, various standardized tests, I can't recall off the top of my head if they use fine tuning for those specifically. You certainly could. That is an approach that you can use. And whether they did or not, I think it's reasonable to think of fine tuning as an approach that would be applicable to that type of use case, because you have a bunch of question answer pairs that you can fine tune on to optimize yourself to, perform well. I think the researchers, that might be a good way to do well on those benchmarks. But I think the academic community wants to be able to do well without fine tuning. So I think a lot of the research kind of was like, we got these results despite not training on this data set specifically.
Right.
That was a really big point in the literature. Not to say that you couldn't fine tune, but it was just kind of like part of the intention was it's a generally applicable model.
So let me bring this home to for a second. So at eye level in our RAG tool set, we built this RAG pipeline. We make it very easy for you to do RAG, and one of the things that is unique about it is that we can handle very complex documents. You can ingest documents that have tables and forms and graphics and all kinds of things that typically confuse language models and cause them to hallucinate, at least at scale. To achieve that, what we did was we took essentially, as you say, a generalized vision model that was good at detecting objects in general, and we fine-tuned it. We trained it on 1 million pages of documents from legal and medical and government and so forth, so that now when you upload a document to it that it's never seen before, it's not specific to how it was trained, it's able to generalize it and find the tables and forms and objects on these complex pages, even though it's never seen that particular document or one like it before. Am I on the trail here? This is basically the core of what we're talking about.
Yeah, I think so. Like training and fine tuning and generalization, like you can think of maybe that document model that we fine tuned is better at general stuff because it had that general pre-training, but it's better at the specific task because it was fine tuned. So there's like a give and take between the two approaches.
Right. I know a lot of the issue, maybe we didn't get into this, is, that fine tuning set is really important. It has to be balanced, or it could wind up, in our case, being too tuned towards medical or too tuned towards financial, and then something kind of falls apart and doesn't work. And I know multiple times we had to like take a step, roll it back, say, wait a second, the documents we fed it are kind of unbalanced. Let's roll this thing back and then try it again, try a more balanced set of information to feed it. Our version of question answer pairs, which are essentially documents with labels on them.
Yeah, and to wrap this up in a nice bow, because I think you're describing it really well, fine-tuning is a great way to get that heightened level of performance, but it's not easy.
Yep.
So
what's next? What's next on the education?
Yeah. So we talked about fine-tuning. This is how you fine-tune in a nutshell, right? You do stochastic gradient descent on a pre-train, and then you do stochastic gradient descent again on a fine-tuning data set. And that's fine-tuning. But actually, really, fine-tuning is usually not done this way. Oh, I'm going back and forth. I'm not going to zoom in. so I'll just describe it. It's fine. So this is more of a conceptual diagram anyway. So we're good. So we talked about gradients before. So I want to dig a little more into. Can I zoom in? I'm not gonna try. I want to dig a little more into the training.
I believe you can zoom. I just believe in you that you could figure this out.
Wait, hold on. Okay. All right. I'm not going to move from there.
You just need confidence, man. You need a boost. That's all. Look what you did.
Yeah, I didn't move. I think if I zoom, it like changes the slides. So I want to zoom in, no pun intended, on like the training process, and we said stochastic gradient descent. So when you pass data through a model, it makes some prediction, but it doesn't just make a prediction. It also calculates something called a gradient. And it does that for every single parameter, learnable parameter in the model. It goes, if this output should be bigger, then this parameter should be bigger, or this parameter should be smaller. So you can think of these as like gradients as a bunch of road signs, where if you want this output to be bigger, this parameter has to be bigger, this parameter has to be smaller, and you keep track for every parameter, these road signs, right? So when you make a prediction in training, you make a prediction, you calculate the gradients, then you compare the prediction to what it should be, right? So it should have been dog, but you said cat. So the value for dog has to be smaller. The value for cat has to be bigger. Let's look at our gradients to see, hey, how do we update our parameters to make it more cat and less dog?
Okay.
So the gradients tell you how to do that change. Now, if I can, all right, if I zoom out and then I zoom in here, and it's fine. So there's a trick you can do. And this trick is, at first it seems kind of silly because you do more operations and it takes more space and it's more complicated. So why would you ever do it? But it's a concept that got built on into probably the most powerful fine-tuning approach that exists. So imagine, so you have your parameters. Instead of changing your parameters, what if you kept track of the changes of the parameters separately? So instead of like updating the parameters themselves, you freeze them. This is a common symbol in AI where you say we're not updating these during training. They're just used to generate the prediction. And you basically initialize a big matrix of zeros. And then you say, we're going to make a prediction based off not only the model parameters, but these change parameters. And we're going to add them together, calculate our loss on that, then update our change matrix. So instead of updating the parameters themselves, we'll update the change matrix. It's exactly the same at the end of the day. You're changing your parameters to get different predictions, but now you're just keeping track of them separately.
This would be like editing a photo and it's lossless. You can continue to make changes to the photograph, but the changes you make are stored separately. The original data is never changed.
Exactly. And I'm not gonna read this whole thing. There's a paper called LoRA that basically said, when you're traversing this landscape, it's good to have a bunch of parameters. And there's this concept in AI called an over-parameterized model. You have more parameters that you need, and we see it all the time. Like we have models with trillions of parameters now, like a crazy amount of parameters. And one of the core theories in AI is maybe you don't need these parameters here. Maybe the point of these parameters is so that you traverse the landscape better. Then when you end up here, really it's just kind of extra baggage that you just needed to get to this point. maybe there's a lot of duplicate information in these parameters somehow once you actually get to the point where you've learned something.
Okay.
And this is where something called low-rank adaptation comes in, which is LoRA. You may have heard of it. It spawned various derivative fine-tuning strategies. It's probably the most popular and powerful fine-tuning strategy. Basically, it says after you've pre-trained the model, a lot of those parameters, you don't really need to update them for fine-tuning. Like when you fine-tune, we're like steering the ship of the model usually. We're not like totally rebuilding it. We're just moving it around in little ways. So the idea of LoRA is, what if instead of this change matrix, like learning changes, what if we learn a decomposition of the change matrix? So you basically say, we're going to learn these two tiny matrices, and we're going to multiply them together to create the change matrix. And that means instead of 1, 2, 3, 25 parameters, you're learning 10 parameters. And so basically, the way LoRA works is when you pass your input, you pass it through the change matrix, you add them together, you get your output. Except your change matrix doesn't actually exist. It's really the multiplication of these two tiny matrices. And this is a really clever sort of subversion, because if you have a low rank, if these matrices are small, and if you have these big matrices in transformers, which transformers have massive matrices, you can train on a practically relatively insignificant level of parameters to completely change the model. I ran LoRA on a relatively small model, and I ended up training on 0.14% the parameters that I would have trained otherwise if I trained the entire model itself. And that results in, one, faster training times, because you end up being to do less calculations if you end up doing this kind of cleverly, but also saving the changes. You can save your model changes in this incredibly small format, and you can save them separately from the model itself.
This feels like a form of compression.
It very much is. Low-rank adaptation is essentially learning compression strategies. And actually, there's a derivative called QLoRA, where basically you compress the model, then you learn a LoRA adaptation to fix any changes that happen from the compression process. So LoRA has like exploded, like in terms of making these models run more efficiently and be able to fine-tune correctly. So there's this kind of cool hyperparameter, and I think conceptually we can kind of tackle this at this point. You can basically, as a parameter, change the amount of what's called linear independence. So basically, your A and B matrices that end up becoming a change matrix for some set of parameters in the model, these can be big matrices, or these can be small matrices, or these can be big matrices. And if the shapes make sense, like the lengths and widths of these two end up in the same size change matrix, but this one encodes more information and this one encodes less information. So you can basically control how compressed these change matrices become with this R parameter that controls how big these decompositions are.
Interesting. And then how do you measure the loss? How do you measure maybe the loss of accuracy that may come from this, extra layer of compression?
So usually kind of what you do is you try a few strategies and you see which one comes out on top. You see when you get diminishing returns. And actually what's really cool about the LoRA paper is their core assumption that change matrices are of low implicit rank, which means they might not literally have a lot of duplicate information, but they can essentially be completely described with duplicate information. That's what low implicit rank means. That core assumption turned out to be very accurate. They ran models across a variety of data sets, and R values of 1 or 2 were usually perfectly acceptable. So like you're like imagine representing, I don't know, a matrix of 1 million parameters with like 500, and then doing that across an entire model, and it actually working pretty well. It's actually kind of like magic.
Yeah. So maybe the business outcome, or the outcome that people really care about, is smaller models that are as good or almost as good as bigger models, which you can run on cheaper hardware, smaller hardware, and essentially take some of the huge amount of the cost out of this AI layer, which has become incredibly capital expensive to run, and hard to run on the edge, hard to run on cell phones, hard to run on laptops. and we're starting to see that change because of this new ability to compress models with this LoRA technique. Is that a correct analysis of the benefit?
Yes, and I think more specifically, something called QLoRA, quantized LoRA, is even more that. But I think that general vibe is totally accurate.
All right, I'm all about the vibes, man. That's generally like
you know me. That's the word of my life.
So I do know you're all about the vibe. It's kind of amazing. I'll ask you like a really kind of like this question, actually, something specific. Like, how do you measure the loss? And you're like, man, you just run a couple times, you get the vibes. Which is kind of what you just told me. We just run a bunch of times and see what happens.
You know, it's funny. In AI, it's because it's so complex and it's a black box. You have to be very scientific, but you do have to be willing to like chill. Like it's like seriously though, like to be able to understand in like this abstract sense of like pressures of data, almost like because you can't think of everything in like this multi-billion parameter model in your head, and no one completely understands how they're working. So you kind of go based off. It's almost empathy sometimes, like thinking of like, yeah, how would I think through this problem? And like if I was this model and I was restricted in this way, how would I like not be able to solve this? And what systems can I build to sort of encourage maybe a better learning system? It's actually being a teacher, I feel like has actually been really helpful because you're kind of building a brain and then teaching it. So like having that almost
I feel like smoking a lot of bong hits, man, to figure this out. This sounds like a gummy problem. You just gotta like you got to get deep into math and you just got to like chill and start to pretend you're the model. Get inside it, get empathetic with it, and then relax, get the vibes.
Yeah. You heard it here, folks. Substance abuse is critical in machine learning. So there's kind of a side idea that we haven't discussed yet.
Okay.
But I think it's one of the coolest portions of LoRA. So on the slides, so like we have these change matrices, right? This change matrix, and it's these tiny little matrices, right? So when you fine tune a model, you have to keep track of these tiny little matrices to completely change the model based on whatever you fine tuned. But what's cool about this is because you're not updating the model itself, and because these are really tiny, you can do LoRA a bunch of times, and you can fine tune it on a bunch of different objectives. And then you can just kind of store these tiny little matrices. And basically, this is all the changes you need for fine-tune version A. This is all the changes you need for fine-tune version B, version C, version D. And actually, when you look at like image generation, LoRAs are all over the place because you have this idea of you can now, for a really big vision model, you can now express stylistic changes based off these very little compressed representations, and they can completely change the model to result in all sorts of different styles.
So you need thousands or tens of thousands of images, you might need dozens. And what we're looking at here, I think, is stable diffusion, which kind of popularized this idea, right?
Yeah, so it's not really, I wouldn't say that it's the number of images you need to fine tune. Okay. Like you can fine tune on like a gajillion images. If you have like a bunch of images and you want to fine tune on that, really, I think the punchline is once you've done that fine tuning, you don't need to save an entire new model. You can just save these tiny little representations of how the model changes. And that means that if you have a massive model that takes forever to load onto a computer and then take off of a computer, you can basically use this as like a skeleton. And then if you want the color water. If you want the color water version, you just import these tiny little changes. If you want the arcane style version, you just import these little changes. So you have this sort of skeleton model that can be very large, and you can completely change it based on these tiny little hot swaps. And actually what's cool about LoRA is the hot swaps can be really quickly. You can have a multi-billion parameter model, and hot swapping LoRAs can take a matter of like less than a second. So you can like, if you want to talk like a pirate, you just take your pirate LoRA. Or if you wanted to talk like Einstein, you just import your Einstein LoRA or like whatever. And that basically any AI model, like modern AI model, you can use LoRA for this type of hot swapping.
That's cool. Oh, you could also, to your point from the beginning of this show, you can, if you want your AI to talk like a pirate, you can also just tell it to talk like a pirate.
or you can tell it to talk like a pirate. Yeah.
And give it a couple of multi-shot examples of pirate talk, and it does it, but maybe not with the same fidelity as a fine tune.
Yeah, or maybe to a heightened degree of fidelity. And maybe if you fine tune, then you might encourage some level of catastrophic forgetting that damages the model's understanding in some way. So it's vibes. Well, but you go off like, how complex do you think it's going to be? How much do you think the model really fundamentally has to change to really do what you need? Can you just give it a general prompt, or do you really need it to be specific based on a lot of examples? And you might choose to do LoRA, which is why generally it's recommended not to do fine tuning immediately, but also why it remains a fundamental sort of tool in the tool belt of a data scientist that's building complex applications.
Well, very cool, man. Thank you for this. Thank you for helping me traverse through this latent space, to use the terms, to get through this show. I really appreciate. I felt like, actually, maybe more than any show we've done prior, I just sat as the student and you were the teacher, and that was kind of great. The vibes were fantastic, so I'm very grateful. That's it for this episode of Rag Masters. Thank you, everybody, for tuning in with us. Catch us next time, and have great vibes. See you out there.